Well, let's continue with tachyometric surveying. Uh, when the staff is vertical, the staff intercept AB is not normal to the line of sight, OC. Let's draw line A, B, passing through C and perpendicular to OC, cutting OA at A' point and OB at B' point. In right angle triangle OFC, we can calculate this by this formula. The study here is subtend an angle alpha, and we know that the value of alpha divided by 2 is very small, hence the triangles A'(C) and B'(C) may be assumed to be right angle triangles. And finally, we can calculate the distance d. It's horizontal distance as ks cosinus q plus c cosinus theta. And vertical facet of the triangle, you can see the formula of its calculation. Another option where staff is normal to the line of sight. As the staff at E point is held normal to the line of sight, AC line, therefore the staff intercept AB in normal to line. So we can easily calculate the final formulas to calculation the horizontal distance and vertical distance. And the last option, when the line of sight at an angle of depression. Here you can see the formulas. Another possible option of obtaining of calculations the distance between the tachyometer and staff is so-called movable hair method. As discussed in the study, hairs, if the study hairs are fixed, the angle B between the ray along the upper stadia that along the lower stadia is also fixed. The staff intercepts varies with the distance of the staff from the instrument if the stadia hairs are movable, and the staff varies intercepts as distance is kept fixed. The tachyometer angle B changes with the staff position. The diaphragm has an arrangement for the measurement of the stadia interval accurately. Each hair of the stadia diaphragm can be moved independently by a separate sliding frame. Here you can see examples of calculations the distances between tachyometer and staff. Any combination of these equations gives the same result, showing that the telescope is analytic over this range to all intents and purposes. Here you can see the same picture, same figure in the bigger scale. The tachyometer, the staff, the distance between hairs of the crosshairs, and the horizontal distance and vertical distance. Another case, vertical depression angle. In this case, the vertical distance shows us depression between point A and B. Here is example of non-movable hairs. The procedure of distance measuring is as follows. We should select for understanding if the tachyometric constant is really equal to 100, we should check this constant. We should select a line about 100 meters apart on a fairly level ground and mark the intermediate points from the starting at the constant intervals, for example, 20 meters, 20, 40, 60, 80, etc. These distances must be measured accurately using a tape with much more precision. Then we set up the tachyometer on the starting point, center, and level it. Observe the staves at each intermediate stations, keeping the telescope horizontally, and obtain the intercept S1, S2, etc. Then we substitute the values to the tachyometric equation and obtain the values for the constant. Or obtain the values graphically as follows. Errors in tachyometric surveying. We have three kinds of errors. First of all, instrumental, then due to manipulation and sighting, and natural errors. The natural errors are most dangerous. Well, these natural errors are made by different atmosphere effects and natural environment around the surveying area. Well, instrumental errors mainly include the following: imperfect adjustments when the instrument is not good. All these geometric interrelations among the axes, and so you can take care of your instrument. The second one, irregular graduation of the staves. This error can be overcome by measuring this graduation with special small, very precise ruler. The third one, incorrect values of the tachyometric constants. It is advisable to determine the concepts before the observations. Human errors. Well, human errors, we have three kinds of human errors. First of all, inaccurate centering and leveling of this instrument, non-vertically, not verticality of the staves, and inaccurate estimation of the stadia intercept. These human errors can be common for young surveyors, but while you become much more get much more experience, these human errors become smaller and smaller. And the natural errors, refraction and expansion of the states. Well, the refraction, we also can overcome the refraction while use make our tacheometric surveying in the when the weather is appropriate, good enough for surveying. We should not walk in the field about 1 hour after the sunrise and 1 hour before sunset. And also the hours closer to the noon, to the 12 o'clock, is also not very good for surveying because of heat outside in the summer. So we can speak about the best period of observations. And the last one source of errors is expansion of the states. Well, for much more precise work, we use much more expensive metal staves with invar tape on this stuff. Many of the errors of the study are common to all similar operations. Well, it's from another source. Study interval factor is not that assumed. Rod is not of standard length. All these conditions should be overcome while choosing the equipment of good quality. Incorrect study interval. The study intervals varies randomly owing the inability of the instrument operator to observe the study interval exactly. In a series of connected observations, such as traverse, the error may be expected to vary as the square root of the number of sites. Rod is not plumb, not vertical. This condition produced a small error in the vertical angle. It also produces an appreciable error in the observed study interval and hence in computed distances. The error being greater for large vertical angles than for small angles. It can be eliminated by using a rod level. Unequal refraction. Unequal refraction of light's rays in layers of air close to the Earth's surface affects the sight on the lower stadia. Here, more than the side on the upper stadia here. And those introduce systematic positive errors in stadia measurements. Whenever atmospheric conditions are unfavorable, the sides should not be taken near the bottom of the rod. Well, often when the weather is hot, you can probably see when the rod is the picture of the rod is not clear. It's kind of moving quickly because of the heat, because of the hot air rise up. So in this condition, not only refraction but mixture of air occurs, and we cannot get the proper measurement of the distance and horizontal and vertical distance. Another errors in zenith or vertical angles. Errors in vertical circle readings are relatively unimportant in their effects on horizontal distances. For example, uncertainty of 1 minute in a zenith or vertical angle yields discrepancies of 5 millimeters in 100-meter side. Similarly, an error of 1 minute in a zenith or vertical angle of 75 degrees or 15 degrees respectively produce discrepancies for 2 centimeters in 100-meter side. With respect to differences in elevation, analysis of equations reveals that uh, 3 centimeters for a 100-meter side. Uncertainty in a study interval, especially at higher angles of inclination, will have a more pronounced effect on elevation differences than errors in zenith or vertical angles. Here you can see an example for when we have 3 points as in this picture. Well, we are standing on above the point D with instrument, and the staff is staff points are A, B, and C. Our bearings to these points are as follows: vertical angles are as follows, and stadia readings as follows. If the reduced level of D is 150.10, H of instrument is 1.4 meters, and the tachyometric constant is 100. It's required to find the horizontal distance of the staff points and the reduced levels. Find the distance AB, BC, and CA. And here you can see the solution of the problem. Well, for line DA, for line DB, and from line DC. And from triangle DAC, DAC, we can calculate the distance of AC distance as it will be equal to 48 meters, 0.505. And from another triangles, we can calculate BC line and AB line. Here are examples, the same pictures of tangential horizontal line of sight and inclined line of sight, and the formulas for these options. Another interesting decision for tachyometry is not modern nowadays. Maybe this kind of so-called self-reducing tachyometry is not so common because of electronic tachyometry much more wider, use much more wider. Let me explain you the peculiarities of this method. The RGS is one of the rare theodolites Wild Corporation produced. It was a successful attempt to create a self-reading tachyometer that would not simply give the slope distance to the assistant holding the vertical reference staff, but the horizontally reduced distance and the height difference. The abbreviation RDC stands for Reduction Distance Meter for Vertical Staff. RDS tachyometry is a method of surveying used to determine horizontal and vertical distances between survey points. In the RDS tachyometry, the surveyor sets up the tachyometer at known location. Well, I will show you. The leveling staff special leveling staff that has an extension rod at the bottom, and the staff is read using the special curved crosshairs of the instrument. With the extension rod of the leveling staff set at the instrument height minus 1 meter, so at an instrument height of 1 meter 0.34, the rod was set at 0.34. We have three special hairs in auto-reduction tachyometer: elevation pointer, fixed pointer, and distant pointer. You can see, and these crosshairs automatically marks on the rod the distance and the phase difference between instrument and rod. The vertical angle of the telescope is adjusted until the zero line of instrument runs over the 1 meter mark of the staff. The uppermost line gives the horizontal distance to the staff, while the height line of the middle one shows the factor to multiply its reading with to get the Hertz difference. Plus 0.1, we just multiply to the reading 21.7, it means 2.17 meters, as you can see in the picture. Here you can see the examples of the when we raise the telescope up and down, the different crosshairs appears in the tube. So it was a convenient method of tacheometric surveying. Distance curve, factor, height curve, and zero curve. Initially, north direction will be determined by compass, and which is established in the field, and then centering and leveling should be done. The following readings are taken in this approach: height curve, distance curve, zero curve, factor, and horizontal angle. You can see the horizontal and vertical angles in the special microscope window. Here you can see equations for RDC tacheometry. Now, so to conclude, we have few possible methods of distance measuring. First of all, direct and indirect methods. Direct methods where means we use equipment that we should put directly in the line that we should measure. First of all, it's taping. It's not convenient method for long distances because mostly tapes are not very long. 20 meters, 50 meters, and this is all. 100 meters, the tape will be very, very not convenient, very big. Another option is odometer, is not very precise. Well, indirect methods. Electronic tacheometry, we will speak about this method soon. And namely tacheometry, stadia method, substance bar, and range finder. Electronic distance meter, we have two options, electro-optical and microwave electronic distance meter. Well, what does it mean, substance bar tachymetry? Substance bar is identified as horizontal stave, which is used for measuring both the horizontal as well as vertical distance in places where chaining or using tapes is not convenient, is impossible, and so on. Substance bar can be used where some locations cannot be reached to measure the horizontal distance. Well, we stand the substance bar on a tripod. We use spirit level to make this substance bar horizontal. We use alidate to change the direction of the substance bar directly to perpendicular to our orthogonal to our line of sight. The size of substance bar system is 2 or 3 meters. Here you can see in the pictures how does it looks like. The width of substance bar should be 2-3 meters, but commonly 2 meters width of substance bar is practiced in tacheometry surveying. In this practice, stuff intersects is called as base because the size of the substance bar is constant. When the base is horizontal or substance bar is horizontal, that is known as horizontal base substance method, and angle is measured with the horizontal circle of the theodolite. If the base is vertical, the method is called vertical base substance method. It is a physical bar sighting targets at both ends. The distance d between the target is known. The bar is set up on a tripod at one end of a line, centered and perpendicular to it. At the other end is a transit or theodolite. So, in this case, we can measure theta angle. The opposite side of triangle is S. So we can take the readings of 8 right hand target, middle target, and left hand target. And then using trigonometric formulas, we can calculate horizontal distance. Here you can see the formulas. The L is the size of the substance bar, when the D in every case is 0.5 L divided by tangents of 0.5 alpha 1 and alpha 2. Another option, we can derive equation for computing distance by substance. 0.5 L cotangents this angle divided by 2. What value would you choose for L? Well, the schematic diagram of the substance bar having center at C fitted with the targets A and B. Here you can see the same explanation. The same formulas. Well, for distances up to 80 meters, we can use the simple target bar. Substance bar. For distances from 80 to 160 meters, we can put the substance bar in the middle of the line and measure distances from opposite sides of the line. And then we calculate, summarize D1 and D2 distances. You can see example. Well, measurement on horizontal distance and elevation on sloping ground by substance bar. Mhm. Here all the explanations. You can here see these explanations. Well, for distances from 160 meters to 350 meters, we can measure uh, the auxiliary distance between and we use two theodolites. Theodolite 1 measure beta angle and theodolite 2 measure auxiliary baseline, uh, which is perpendicular to the main line. Here you can see formulas. And finally, for distances from 35 to 800 meters, we can make such schemas for line measuring. Well, all these methods are quite not common nowadays. Nowadays, the main method is electronic tachyometry. The study procedure is used less and less often these days. More commonly, geomatic engineers use a combination theodolite and electronic distance meter, known in jargon as a total station. Total means that this total station is able to measure all the necessary dimensions. The distances, the angles, and the vertical distances. Often these instruments are connected to a field computer, which stores readings and facilitates the processing of the data electronically. This instrumentation has facilitated the development of this method of detail and counter surveying into a very sleek operation. It is now possible to produce plans of large areas that previously would have taken weeks in a matter of days. The math behind the operation is very simple. It is, in effect, the same as the study of formula with the term of the distance replaced by measured slope distances. Well, electronic distance measurements. Electronic distance measuring instrument is a surveying instrument for measuring distance electronically between 2 points through electronic waves. The method of direct distance measurement cannot be implemented in difficult terrains. When large amount of variation in the terrain of large abstraction exists, this method is avoided. As an alternative to this optical distance measurement method was developed, still it gained a disadvantage of limited range of measurement. It is limited to 15 to 150 meters with an accuracy of 1 in 1000 to 1 in 10,000. Above all, we have ADM with accuracy in 1 in 105, having a distance range of 100 kilometers. Well, the theoretical base of the method. Sunlight or artificially generated electromagnetic wave consists of waves of different lengths. The spectrum of an electromagnetic wave is shown below. Here you can see wavelengths and frequencies. For uh, distance measuring, we use different wavelengths. For example, visible light, microwaves, and radio waves. Here you can see types of electronic distance measurement instruments. First of all, microwave instruments. These instruments make use of microwaves. The instruments need only 12 or 24-volt batteries. They are light and highly portable. Uh, Tellurometers can be used in day as well as in night. The range of these instruments is up to 100 kilometers. Another option, infrared wave instruments. In this instrument, amplitude modulated infrared waves are used. Prism reflectors are used at the end of a line to be measured. These instruments are light and economical and can be mounted on theodolite. With these instruments, accuracy achieved is plus minus 10 millimeters. The range of these instruments is up to 3 kilometers. And lightweight instruments. These instruments rely on propagation of modulated light waves. Light waves are most suited way in this instrument. These instruments are also very useful for civil engineering projects. During night, its range is up to 2.5 kilometers, and while in day its range is up to 3 kilometers. Accuracy of these instruments varies from 0.5 millimeter to 5 millimeter per kilometer distance. From the transit time and known velocity, the distance can be easily measured. Now to solve the problem arise due to difficulty in starting the timer at B, a reflector can be placed as shown below instead of a receiver at B. So we measure the distance twice, forward pass and reflected pass. The reflector reflects the light directly to the uh, generator of the electromagnetic waves. In electronic distance meter, the beam of light is the carrier and which is reflected back from the mirror located at the other end. Such instruments are less expensive because one active instrument and battery are only needed at one end of a line, and instrument at other end is simply a reflecting mirror centered over ground's center mark. So we have transmitted beam, reflector, and reflected beam. By the 1970s, relatively small, lightweight, and easy-to-use electronic distance measuring devices called EDMs were in use. The advance of technology and miniaturization of electronic components enables the building of theodolites that measure angles electronically, called electronic theodolite. Combination of an electronic theodolite and electronic distance meter and software running on an external laptop computer known as a data collector called total station. And the another popular technologies are the global positioning system, was designed for military applications. Its primary purpose was to allow soldiers to keep track of their position and to assist in guiding weapons to their targets. A computerized database management system for capture, storage, retrieval, analysis, and display of spatial data we called GIS. Handheld electronic data meter, distance meter. This kind of equipment is very handy, cheap, can be used with accuracy of 10 millimeters or so, rapid measurement, long range, high accuracy measurement of moving target. Electronic theodolite for precise surveys, the vernier theodolites are replaced by modern theodolites such as optical and electronic theodolites. The electronic theodolites have optical system to scan both horizontal and vertical circles and display them digitally on a screen, as you can see in the picture. The basic principle of a total station integrates the functions of a theodolite for measuring angles and electronic distance meter for measuring distances, digital data and data recorder. All total stations have similar constructional features regardless of their age or level of technology, and all perform basically the same functions. These instruments are measuring the distances of prism poles mounted with prisms with the help of laser beam or infrared rays. These signals are emitted by the instrument EDM and reflected back to instrument by the prism mounted on the prism poles. The time interval between emission and receptions helps to calculate the distance as the speed of these signals are precisely known. Well, d means distance, t total time taken, and v velocity. Total station, total solution for surveying work, most accurate and user-friendly, gives position of a point x, y, and z, mm, known point, base point, measures distance and angles and displays coordinates. EDM is fitted inside the telescope. You can see the telescope is much more bigger as usual. And we have digital display to display the result of measurement. These total stations have onboard memory to store data, compatibility with computers, measures distance and angles and displays coordinates. Outer level compensator is available and can work in lesser visibility also. Can measure distances even without prismatic target for less small distances. They are waterproof. Onboard software are available. Can be used for curve layout after feeding data. These total stations can be used for wide variety of purposes. General purpose is angle measurement. Another general purpose distance measurement, slope measurement, provising of control surveys, uh, counter and detail mapping, and setting out and construction work. Angular accuracy is up to 1 second of arc. Distance measured with laser up to 2 kilometers. Distance measured with infrared rays up to 4 kilometers with single prism. Capable of storing up to 20,000 points. Here you can see the prisms, the tripod, and the total station in a box. Here you can see the interface cable to a computer and highly precise measurement of distances and mm, angles. The components of a total station is electronic distance meter, uh, electronic theodolite, onboard microprocessor, data collector, data storage, and prisms. Microprocessor averages multiple angle measurements, averages multiple distance measurements, computes horizontal and vertical distances, and calculate corrections for temperature, pressure, and humidity, and computes all the x, y, and z coordinates of a target. Uh, Here you can see example of specification of different total stations. Here you can see a prism target. Advantages of total station over conventional instruments. Traditionally, traditional survey methods are laborious and time-consuming. Fully automatic electronic measurement, digital display of staff reading and distance, data storage is possible. Direct transfer to a personal computer of data stored in instruments, online operations through integrated interface to computer. Disadvantages. Total stations depend on batteries and electronics. The LCD screen does not work well when it is cold. Battery life is also short. Batteries and electronics both don't work well when wet. Loss of data is an important consideration. And recent developments include a GPS unit with the total station, fully integrated data storage and data processing, Bluetooth data transfer, or GPRS transfer. Main errors in electronic distance measurements are very similar to errors while we make surveys with stadium method. First of all, personal errors. Inaccuracy in initial setup of EDMs and reflectors over the preferred stations. Instrument and reflector measurements going wrong. Atmospheric pressures and temperature determination errors. Instrumental errors. There are calibration errors, chances of getting maladjusted time to time generating frequent errors, and errors shown by the reflectors. And natural errors, atmospheric variations in temperature, pressure, as well as humidity. Microwave EDM instruments are more susceptible to these multiple refraction of the signals. Well, the advantage of using EDM instruments is the speed and accuracy in measurement. Several obstacles to chaining are automatically overcome when these instruments are used. In the picture you can see the schema of the measurement. Total station measures distance using a microwave or light wave. Also, total station measures vertical and horizontal angle and calculates while the coordinates of point B is known, the total station calculates the XYZ coordinates of point A very quickly. Here you can see a few interesting examples of remote elevation measurement. Well, for example, we use remote elevation measurement while we need to measure the height of electrowaves or electrowave wires. Well, it is not possible to get to these wires directly because of high voltage. So we stand the reflector just beneath the wires. We measure the horizontal distance and the vertical angle, and the heights to the wires can be calculated. A prism reference point is set directly below the place to be measured, and by measuring the prism, the height to the target object can be known. This makes it easy to determine the height of electric power lines, bridge suspension cables, and other large items used in construction. Another option, remote distance measurement. We can, with remote distance measurement, the horizontal distance, slope distance, difference in height, and percentage of slope between the reference point and the observation point are measured. The distance between one observation point and another one is measured as well. Uh, uh, Next time, I am going to tell you about the uh, rectangle grid on construction field when the future building is constructed. So the total station are often used to prepare the territory for future construction. Well, um, electronic distance meters can be mounted on a different base. In general, EDM can be mounted alone or with another surveying tool. The most popular types as follows: separate unit on top of standards of theodolite, on top of telescope of theodolite, and integral part of total station. The reflectors used with electro-optical type and called the retroreflector. Retro means that the waves goes back directly to the reflector and back to the receiver, using precise prism which can be single or multiple. We use multiple prisms where the distance is much bigger. The maximum distance of measurement of EDM device depends on the design, the quality and number of prisms, the atmospheric conditions. The operation procedure: set up the instrument over the survey station and record its height, and set up the reflector on the other side. Point the instrument towards the reflector using telescope. Adjust the pointing of tangents using the screws of the instrument. Read and record the temperature, atmospheric pressure, then press the correction button. Press measure and record the reading. And this is all. Corrections for zero centering. The constant errors appears in all distance measured by the combination of instrument and reflector. If AB is measured distance between 2 points, and so AC and AB, um, we use correction AB plus C correction. So C can be calculated as AB minus AC minus CB. Correction for frequency. Well, some kind of instrument has errors in frequency. We can calculate theoretical frequency, we knew it, and we can measure real frequency. So the signal frequency also influences the result. Well, the calculation of vertical distance between points using the vertical angle measurement we called often trigonometric leveling. If the process of determining the height difference between 2 points using the measured distance and vertical angles. In this case, the vertical distance is equal to S, slope distance, multiplying cosinus Z, zenith distance. It's angle from zenith direction to the slope distance. Well, and also we use plus y minus t. It's instrument heights and target heights. We can use the equal heights of instrument and target. So in this case, I will be equal to t, and these elements of formula disappear. S means slope distance, Z vertical angle, I and height of the instrument, T is the height of side target. And here you can see examples and practice. Well,